Swayam Prabha. Digital India. Educated India.
So I will try to focus on introducing the mathematics of graphs. Right? So in particular, I'll show you a whole sequence of theorems and properties. Right? So this forms the whole subject of mathematics called graph theory. And as I introduce these concepts to you, I'll also ask you questions about, look, we defined this particular property. How do you test whether a given graph has this property efficiently? Right? So this is the kind of question that I will put into your thought process. So there might be some very minor overlap, right? But we will ensure that the two streams, right? You learn graph theory, the mathematics on one side. The other side, you will learn how to design an algorithm and also think about the implementational aspects of it. Right? In some sense, we will try to show you that this whole subject called computer science is essentially two parallel streams which run together, which feed each other, right? So one is the underlying mathematics, right? And the other side is designing the algorithm and implementing them, right? And that's something that we will try to, or at least I will try to communicate as a theme repeatedly, right? So that it's not just the algorithm that is important, it's how you implement it, right? It's not just the implementation which is important. How do you analyze it? To analyze it, you need the appropriate world of mathematics, right? So therefore, this whole thing is very important. Therefore, it becomes like a subject like physics, right? So you don't have to think of it like computer science. I mean, you start studying Newton's laws of motion, which I'm sure all of you have done. Then they tell you that, oh, you have speed, but speed is insufficient. You also have to have direction with it. Then it becomes a velocity. Then you need to introduce an abstract object called vectors. Then you have to do vector algebra, right? And so on, right? So this subject also has the same attributes and properties, right? So if you keep this in mind, then learning the whole subject becomes a full task, right? So you learn the underlying mathematics, you learn how to write programs, right? And then you learn also how to design the intermediate algorithms. If you see, now you become an engineer, right? So you know the mathematics, you know how to make something work, you know the underlying laws that make it work. Right? Those are the three steps which are also there in computer science. So it's not that computer science is very different. Finally, what distinguishes it is that the kind of mathematics that you use in computer science, at least so far, is very different from the kind of computer science that you end up using in electrical engineering or mechanical engineering. Right? In mechanical engineering, electrical engineering, I'm sure you've spoken to some of your friends, they'll always be doing some integration, they'll be doing some differential equations, whereas you will always be doing mathematical logic, never more or less using integration at all, right? Unless you're writing a research paper or something like that. Right? Similarly, computer scientists always, programmers always work in AC rooms, they never get grease in their hands. Right? Whereas you go to a mechanical engineer or electrical engineer, that guy will get shock or he'll put his finger inside some device, he'll have a cut finger and so on. Computer scientists have no such problem, have thick specs, they cannot sleep at 9 o'clock in the night, they will sleep only at 1 o'clock in the morning. Right? So there is a big, I mean there are all similar differences, right? So what I'm trying to communicate to you is that this is a subject which is not different from any other subject, right? And we'll try to see what are all the interesting aspects of it. So coming down to graph theory, one of the reasons that you should definitely learn a subject like graph theory is that as you study this subject, right? So as a computer scientist, you probably interact a lot with graph theory. There will be two overarching themes, right? When you learn the subject, one is logic and the other is reason. And if I also like to teach the subject because when I do these proofs and when I show these theorems, I actually show you that you can be logical more or less in any domain, right? And that you can apply reason more or less in any domain. Right? And before I start the first graph theoretic definition, I somehow think that one of the reasons that India is not, for example, a developed country is that we are governed more by fear and faith as opposed to logic and reason. Right? Write these two things separately in your textbook, right? Look at it every morning and you will see that throughout our country, the driving force for our lives is just two things. There is fear and there is faith. Right? If you go to a country like Germany, right, or even the United States of America, I say even the United States of America, right, you will see that the driving force for their lives, right, or the designers of their lives is logic and there is reason. Right. I won't say more about it, right, so you can interpret it, and you will see that graph theory is one place where there is no need for fear, there is no need for faith. There is absolute purity in the sense that everything is logical and every conclusion that you come to is based on some reason in that framework of logic. So in that sense it is very beautiful. So let's start off with applying graph theory to many things. I have seen very old books written in the 1940s, right, about graph theory. The titles of those books were The Theory of Points and Lines, right? And the authors of these books are very famous mathematicians, Doyle and Snell. You can Google this title and then you can Google Doyle, D-O-Y-L-E, and Snell, and you will find this, right? So essentially, a graph is a representation. It's a representation of relationships. Representations of binary relationships, okay, on so therefore, whenever you think of a graph, you think of a representation. So this is quite obvious, I'm sure many of you know this, but the things that you probably never thought about are the connections to discrete mathematics, right? A subject that I'm sure many of you have studied, right? So graph is a representation. There are points, right? These are also called vertices, right? And every edge is actually a binary relationship, right? When I use the word binary relationship, you should immediately think about, in discrete mathematics, you should have studied multiple different types of relations, right? Equivalence relations, partial orders, and so on and so forth, right? So the minute you think of this, you will be able to map those mathematical concepts to this abstract picture, right? Which is often a graph where there is a finite set of points, right? And the binary relationships are captured by what we call edges. And the edges are a subset of the set of points which we call V cross V. So as you can see, I am also trying to introduce the formalization. So whenever you see a graph, you see two things. You see a set of points. The graph is called G. V is a set of points, and you see E, which is a subset of V cross V. As you can see, I have deliberately tried not to draw a picture so far. The reason I have not deliberately avoided drawing a picture is that I don't want you to think that an edge in a graph is always only among 2 points, right? You can naturally generalize the notion of a graph to something called a hypergraph, right? If you consider every edge to be some k-array relationship. That is, edges are no longer pairs of points, but edges can also be subsets of points. You can't visualize it in a pictorial form nicely, but the mathematical concept is amenable to good mathematical analysis still. You may not be able to see it as a picture, you may not be able to draw it on a sheet of paper, right? So therefore, I have avoided drawing a picture. However, keeping a picture in a graph for binary relationships, otherwise called simple graphs, right, is useful, right? So you must have seen many pictures of this form. This is a famous graph, right? So many of you may have seen this, right? It's called the Petersen graph, right? If you ever find a property about which you want to experiment about it on Petersen graphs. Petersen graph seems to tell you a lot about many properties. Nobody knows why, right? So it just seems to work, right? Anyway, so this is a pictorial representation. This is an unlabeled pictorial representation, It is also undirected. What relationship does it capture? What relationship does an undirected, what type of relations do undirected graphs capture? Reflexive, symmetric, transitive. Symmetric relationships, right? So therefore, whenever you see an undirected graph, you see that there is no arrow mark, but the mathematical object that it actually represents is a symmetric relationship, right? Depending on the nature of the relationship, you can decide whether you want to say that the relationship represented is transitive or not, right? Is it reflexive or not, right? So if it's reflexive, then some of you might have studied in graph theory that you can capture this by drawing a self loop, right? And so on and so forth. But the most important takeaway from this about 7 to 8 minutes of talking is that graphs represent relations, right? Relations are what we studied in discrete mathematics. There are some types of them. Every relation has one of these three properties or combinations of them: reflexive, symmetric, and transitivity, right? A directed graph, right, captures, an undirected graph captures a symmetric relationship, whereas in a directed graph the relationship represented need not be symmetric, right? So for example, if you want to represent the parent relationship between two people, that's obviously not a symmetric relationship, right? But a sibling relationship, right, is a symmetric relationship, right? Now this is a story of binary relationships. But today with social networks and so on and so forth, you have already seen that communities have leaders, right? So a community, people being part of a community can be thought of as a hyperedge, right? And therefore you can have hyperedges capturing community. So when I mean hyperedge, I don't mean anything scary or complicated. Like a binary relationship is between this pair, right? A hyperedge is only a subset of vertices. Right? For some reason you put them all together. Right? So therefore this is the whole basic template that we work with. The pair of sets, right? So one is a universe, the set of vertices, the other one is, in this case, pairs. Hopefully as we go through this course, I will show you cases where the edges are no longer just pairs of vertices but larger sets, right? And we will try and associate meaning with them. So let's quickly see the kind of reason, right, as to why you need this abstraction, and then go down to properties of a graph and then prove some theorems about properties of graphs. So essentially this whole business is about asking the right kind of question and thinking about the right kind of questions. When I mean right, there is no single right, the interesting kind of questions, that's what I mean, right? So you can ask, it's a very natural reason as to why you want to represent a road network as a graph, right? So you have a road network and you've designed it. Most likely a civil engineer has designed the road network, right? Taking into account some town planning rules and so on and so forth. At the end of it, you want to know if 2 points are reachable, right? Obviously some of you are thinking in your mind that this must be a very easy exercise because the roads have been laid and they must have been laid very carefully or something like that. But if I tell you that I have a vehicle whose height is about 7 meters, right, then reachability is no longer very easy exercise, right? Because you may have bridges, over bridges and so on and so forth, while a physical road may be there, right? For a vehicle whose height is about 7 meters, right, carrying some very large thing, right, probably cannot go through certain roads, it can only go through certain roads. Therefore reachability becomes a very, very interesting exercise, right, as to whether there exists a usable path between two places, right? So when I mean reachable, you have a road network, reachability is very clear, right? From a starting point, let me say V1, to a destination point, let us say Vk, let us call this T for terminus and S for source, I say that S and T are reachable if there is an intermediate sequence of points V2, V3, Vk minus 1 such that this forms an edge called E1 in E, this forms an edge called E2 from E, and so on up to Ek. So then we say that there is S and T are reachable from each other. Right? So this is a natural question to ask. To design an algorithm to analyze properties of reachability, it is very useful to model the network as a graph. Right? Okay. Now, sometimes you might also want to add an additional attribute, which is a weight function e to a set of positive integers. Right? So, for example, the weight might actually denote the distance or the length of the edge. The weight could also denote the heaviest vehicle that can go on that particular road. The weight could also denote the height of the tallest vehicle that can go on that particular road, and so on and so forth. Right? So therefore, this weight information can model multiple other problems that you would want to pose, right, to this particular thing. Weight could also model the inclination, right, and then you can ask questions about whether you can go by cycle or not. The existence of a road does not mean that you can go anywhere, right? If you're going by a bicycle or if you're going by a TVS 50, you obviously cannot expect to say drive in Ladakh or something like that, right? So unless you have an appropriate bicycle, right? So therefore, you can model multiple questions as graph theoretic questions. Let's pose one more question which looks very different. So many of you may already know this. This is finding a path, right? Let's pose another question which looks very different. Okay. So this is, I'm going to draw this pictorially, right? So this is kids plus addresses, and this is schools plus addresses, right? So the address of one particular child here, the address of the corresponding school here gives you an implicit distance between the child's home and the possible school in which the child can study, right? So this is the picture that I am going to draw as a graph, right? As you can see, the information, the constraint information is only between children and schools, so there are no edges in this picture among the children at all. Similarly, there are no edges among the schools at all. Fine. This is a special kind of a graph, but we won't worry about it at the moment, but we will visit it at some point of time, right? So therefore, there is a distance information. The distance information is captured by address to school. This edge might also be capturing the preference of a kid for a particular school, right? So the presence of the edge, the child or the child's family rank orders the edges, not just based on distances, but some quality measure, right? School 1 to school M, if there are M schools on this side. Right? The schools also rank the children, right, based on some measurement that they have done of the children, right? So this is the ranking of each school on child 1 to child N. Right? Now you can pose a whole set of problems, graph theoretic. You can ask this framework can help you model a whole set of very interesting and practical problems. Right? So can you assign the children to the schools such that every child has to travel as less possible distance to the school as possible. Fine. The schools may also have capacities that makes the problem even more challenging. Right? So so therefore, in which case you want to now say map the children to the schools so that the school's capacity is not violated. That is, if the school can hold only say about 1000 students, right, you should not allocate more than 1000 students to that school, right, and the children should not travel an unduly large distance, not the shortest distance anymore. For example, if this child's nearest school is just 1 kilometer away, but that school is full, the child should probably get a school which is 1.5 kilometers away or 2 kilometers away or some next shortest. So it must not be unduly large, right? However, the ranking also may depend on so many other metrics, right? So you would also want to ensure issues of fairness, right? For issues which are central to different societies, right? So essentially, this is a classic problem where you want to match users and preferences to minimize or minimize dissatisfaction or maximize satisfaction. Right? Observe that these are all English sentences, but the underlying graph theoretic structure allows you to model them mathematically and allows you to write programs, design algorithms to solve them and give guarantees. So let us ask a very simple question. Paths are very clear to you. Let us start off with a very toy question. Are there vertex disjoint edges, and if so, how large is the set of vertex disjoint edges? So please pay attention to the words that I use, right? So this is a graph, right? I showed you that the graph can be used to model multiple problems. I want to introduce to you a concept which is very different from finding paths, right? To introduce that concept, I am drawing a graph and I am asking you, right, does this graph have vertex disjoint edges? Give me edges, no two of them share a vertex. That's why I call them vertex disjoint edges. I'm sure many of you can see them. So you can see that if you choose this edge, and this edge, right, they are all vertex disjoint. Right? And I'm sure you can also see that you cannot choose, right, one another edge without it being sharing a common vertex with some other edge. That is, 3 is the maximum number of edges that you can choose such that any pair of them are vertex disjoint. Right? Because there are only 6 vertices. Right? So it's a small counting argument. Right? So such a structure is called a matching. Why is it called a matching? Because you can visualize, right, that this vertex is matched to this vertex, or this child is matched to this school, this child is matched to this school, and this child is matched to this school. Right? And this is the reason for using the word matching with this. You can look at these vertex disjoint edges and you can group them, one end of the edges as one group, and say that these are all matched to these vertices. Right? So a matching is a set of matching is a set of vertex disjoint edges. And as you can see, the allocation of children to schools can now be posed as a graph theoretic question where you want to match children to schools, right? Or you want to match every child to one seat in a school. Some of you may be wondering, children are here, schools are here. One child can go to one school, but many children can go to the same school. But because the schools have capacity, you can think of matching the children to seats in the school. A child can go to a seat and seat can take only one child. So allocating children to schools can be thought of as finding a matching in the appropriate graph. Right? Very different problem compared to checking if there is a path. Right? And we will study, right, such problems in the world of graphs. Right? But this would be the general theme, right? So what have I done now? I have given you two examples. There are many more such examples, right? So graph theory is not short of the kind of questions that you can ask on graphs, right? So are there paths? Are there matchings satisfying different kinds of properties? These are the questions, two very example questions that graph theorists ask. There are many more such questions, right? Some of you might have seen some of these questions also. So matching is the second one. The third one, you must have all seen the TSP problem, right? So TSP problem stands for the traveling salesman's problem. Well, TSP stands for the traveling salesman's problem, right? What is the problem? You are given a graph. Can you find one big cycle, right, that starts at a place and comes back to the same place, right? It's a variant of checking if there is a path, right? You might also have played this game. Right? You might also have played this game in school, right? So when you are bored with the teacher, right? So where you write, somebody says, can you draw this picture without taking your pen off the paper, right? So such a graph is called a Eulerian graph, right? It's attributed to Euler, E-U-L-E-R, actually pronounced Euler, right? So the point that I'm telling you is that, the point that I'm making is that many practical problems that you see, right, can be modeled as graph theoretic problems, right? Chemistry, for example, right, is full of graph theoretic problems because people want to know, right, if I give you a certain molecule, right, what shape does that molecule actually take in 3 dimension, right? Given the fact that molecules cannot be too close to each other, they can't be too far from each other, and so on and so forth, what shape does this take? And this is very important in questions about finding the structure of proteins, for example. There's a whole body of research where graph theory is used to study how proteins actually fold. Protein is just essentially a sequence of amino acids, right? Depending on the medium, the protein functions in a certain way, and the functionality of the protein is closely associated to its 3-dimensional shape. Right? So people want to understand, using graph theoretic techniques, right, how to find out what are the shapes that a DNA sequence will take, right, when it is in a certain situation, right? So it's a fundamentally graph theoretic question with significant application, right, in studying biochemistry and so on and so forth. Right? So we won't talk about motivation for the rest of the classes, right? Or at least I won't talk about motivation for the rest of the classes. I will assume that you are convinced that the abstract entities that we will introduce are indeed very interesting and useful, right? If not for anything else, they are useful because they are going to tickle your cleverness, right? So that is the framework that I will work in. However, as a student, whenever you see a new graph theoretic concept, it is important for you to ask, what can I do with it? Can I make a small Android application with it? Right? So can I convert it into something that changes somebody else's life? That we can't teach here. Right? That you should practice, right? And that can never be taught.